Good afternoon, everyone. I'm Jinyuan from Penn State University. In this talk, I'm going to present PORE, probably robust recon system against data poisoning attacks. This is joint work with Yupei, Yuepeng, and Neil from Yupei University. Recon systems are widely deployed by many web service platforms such as Amazon, YouTube, TikTok, eBay to engage users, to improve user experience. Typically, a web service platform first collects a large amount of rating scores that the users give to items. Then the web service platform uses rating score metrics to build a recon system that models the complex relationship between user interests and item properties. The recon system recommends the top N items for each user that match the user interests. In the past 2 decades, many recon system algorithms were proposed, such as BPR, IR, NCF, and so on. So next, I will use an example to illustrate recon systems. Suppose we have 4 users, U1 until U4, and 5 items, I1 until I5. This is rating score matrix, where each entry represents the rating score that the corresponding user gives to the corresponding item. For instance, U1 gives a rating score 5 to I1. The rating score is 0 means the user did not rate the item. Given this rating score matrix, we can use a recon system algorithm to build a recon system which recommends a set of top N items for each user. In this example, only a single item is recommended for each user. For instance, for U1 and U2, the recommended item is I5. For U3, the recommended item is I1, and for U4, it's I3. However, it's well known that recon systems are vulnerable to data poisoning attacks. In particular, an attacker could inject some fake users into a recon system. For instance, an attacker could inject fake users by registering and maintaining fake accounts in web service platforms such as Amazon and eBay. In our work, we consider an attacker could inject at most E fake user, and we consider each fake user could give an arbitrary rating score to an item. And also, each fake user could rate as many items as the fake user wishes. As a result, a poisoning recon system makes attack derived arbitrary recommendations. Next, I will use an example to illustrate data poisoning attacks to recon system. This is a poisoning rating score matrix. U5 is a fake user, and the rating scores with red color are given by U5 to the items. When we use a recon system algorithm to build a recon system upon this poisoning rating score matrix, the recommended items for non-fake users or benign users are affected by the fake user. So in this example, the recommended item for U1 and U3 are affected by the fake user U5. So to defend against the data poisoning attacks to recon systems, many defenses were proposed. Existing defense can be categorized into empirical defense and probe defense. Empirical defense aims to build empirically robust recon system against data poisoning attacks. However, the major limitation of empirical defense is that they cannot provide formal robustness guarantee, which means they cannot guarantee their performance under arbitrary data poisoning attacks. Existing probe defense, such as bagging, are mainly designed for classifiers. We find that they achieve suboptimal probe robustness guarantee when extended to recon systems. The reason is that a classifier usually only predicts a single label for a test input. By contrast, a recon system could recommend multiple items for a user. So in our work, we propose PORE, the first framework to build probably robust recon systems. So our key idea is to build an ensemble recon system. Suppose we are given a rating score matrix we first create multiple sub-rating score matrices, where each sub-rating score matrix contains the rating scores of S randomly sampled users. Then we use an arbitrary reckoned system algorithm to build a base reckoned system upon each sub-rating score matrix. Finally, we use majority weight to build an ensemble reckoned system over those base reckoned systems. Next, I will use an example to illustrate our framework as well as its robustness against data poisoning attacks to reckoned systems. So suppose we have a poisoning rating score matrix. So here U5 is a fake user. We randomly sample 2 users. So here is U2 and U4 to create a sub-rating score matrix. Then we use an arbitrary reckoned system algorithm to build a base reckoned system. This base reckoned system will reckon the items for the sampled user. Note that it cannot make recommendations for other users that are not sampled because they are not appear in this sub-rating score matrix. Then we randomly sample another 2 users and build a base reckoned system and use it to recommend the items for the sampled users. We repeat this operation multiple times. As we can see, in the last base reckoned system, this contains a fake user U5. As a result, the recommended item for a non-fake user or a benign user U3 is affected. However, after we take a majority weight, we find that the recommended item for those non-fake users are unaffected or not affected by the fake user. For instance, for U3, the first base reckoned system did not make a recommendation because the U3 is not sampled in the first base reckoned system. In the second and the third base reckoned system recommend I1 for U3, and the last, that is the poisoning base reckoned system, recommend I2 for U3. So after majority weight, the recommended item is I1, which is not affected by the fake user. So we formally show the probable robustness guarantee output. So suppose we have EU, which is a set of ground truth items for user U. And we have LME, which is a set of all possible poisoning rating score matrices when an attacker could inject at most E fake users to a clean rating score matrix big M. Then with probability at least 1 minus alpha, we have the following equation. So here alpha is a very small value, for example, 10 to the minus 3 in our experiments. So this M prime is an arbitrary poisoning rating score matrix in the set LME. And this AM prime U is the set of recommended items for user U by our ensemble reckoned system built upon the poisoning rating score matrix M prime. So this equation means at least RU items in the set of ground truth items will be recommended by our ensemble reckoned system and arbitrary data poisoning attacks with at most E fake users. So we call this RU certified intersection size. We formulate the computation of RU as a following optimization problem. So due to time constraints, I omit the technical details on its derivation process. If you are interested, you could refer to our paper for the details. Next, let's see some empirical evaluation results. We use the movie lens 1M dataset, which contains around 1 million rating scores with around 6,000 users and 4,000 items. We use BPR as a base reckoned system algorithm to build each base reckoned system up on a subsampled sub-rating score matrix. And here is the parameter setting. We set n prime to be 1, which is the number of items recommended by a base reckoned system for each user. N is 10, which is the number of items recommended by our ensemble reckoned system for each user. And T is 100,000, which is the total number of base reckoned systems. And alpha is 10 to the minus 3, where 1 minus alpha is the confidence score. And S is 500, which is the number of users in each sub-rating score matrix. Without data poisoning attacks, precision at n, recall at n, and F1 score at n are standard metrics to evaluate reckoned systems. So precision at n means the fraction of recommended items that are in the ground truth set of a user. And the required n means the fraction of items in the Gong choose set that are recommended. And F1 score measures their trade-off. However, those metrics are insufficient for data positioning attacks because they could be different for different data positioning attacks. And it's very challenging to enumerate all possible data positioning attacks. So in response, we use certified precision at n, certified required n, and certified F1 score as evaluation metrics. Certified precision at n is the low bound of the precision at n and arbitrary data positioning attacks with at most E users. And similarly, certified required n is the low bound of recall, and certified F1 score is the low bound of F1 score. So this result shows our PORE is probably robust against the data positioning attacks. So x-axis is number of fake users, y-axis is certified precision, recall, or F1 score averaged over all users. So as we can see, our PORE can provide a low bound on the performance of our ensemble recommender system and arbitrary data positioning attacks with at most E fake users. We also compare the precision at n required and F1 score at n of our ensemble recommender system with the standard recommender system when there is no attacks. So as we can see, our ensemble recommender system could achieve similar or even higher performance than the standard recommender system without attacks, which means our PORE maintains utility without attacks. This figure shows the time complexity of PORE. So x-axis is number of base recommender systems, and y-axis is training time. So as we can see, as t increases, the training time also increases, which is very intuitive since we need to train more base recommender systems as t increases. We also compare PORE with bagging, which is a state-of-the-art method to build a probably robust classifier. So those three figures show our comparison results. So x-axis is number of fake users, and y-axis is certified precision, recall, and F1 score averaged over all users. So as we can see, PORE outperformed bagging. The reason is that our PORE could jointly consider multiple items when deriving the certified intersection size. By contrast, like bagging can only consider each item independently because it's designed for a classifier, and a classifier usually output a single label for test input. So to conclude, we propose the first framework to build probably secure recommender systems, and our PORE could apply to an arbitrary recommender system algorithm. And our PORE outperforms existing methods extended from a classifier. Yeah, thank you all for listening. I'm happy to take any questions.